Hey everyone, this is BC Polar Notes number 3. So this is pretty much the last concept with polar, but it'll be broken up into two different sections here because it does get a little tricky depending on what equations you're dealt with. But I'll go with it step by step with you guys so that it looks seamless. Okay, and it'll be very easy for you guys to approach it. Anyways, write down this FLT here. You will need a calculator, okay? So here we go. So you're going to be given a polar curve. Specifically, they're called rose curves, and I'll show you that in a second. You're going to be able to find the area while taking advantage of what we call symmetry here. So you guys know what that is. How do we take advantage of it? I'll show you guys in a second here, okay? So there's really two different ways that you can approach areas of polar curves, specifically rose curves. But I'll show you one way that works every time. Okay, there are downsides to it, but I'll show you the pros and cons and I'll let you guys kind of decide there, okay? Okay, so here's a little bit of a review. So remember back when you guys were finding area underneath curves back in AB, when we were dealing with functions, right? What I had you guys do was I had you guys draw a sample rectangle, okay? And then we were squeezing in an infinite amount of rectangles, and that's how we get the calculus, right? When you integrate, you're squeezing in an infinite amount. So with polar curves, since the coordinates are a little bit different, remember, polar curve, you're following the angle, right? So you don't really have a rectangle here. What you have is this theoretical, you travel out a certain amount of degrees or radians, and it creates what we call a sector, aka a pizza slice, right? It looks like a pizza slice. Not a triangle because this end here is curvy, right? So you wouldn't call it a triangle. But this is called a sector. So it's really serving the same purpose as what you guys did back in AB when you're finding areas under curves. So you'll see a lot of similarities there, okay? So here we go. Way back in geometry or integrated math 2, you might have skipped this section. It kind of just depends on who your teacher is, right? To find the area of an entire circle, so meaning finding the amount of space within a circular region, it's just pi r squared. Now, if you wanted a pizza slice or a sector, you only want a piece of the pie. Okay? So what's happening here is I'll use S for sector. Pi r squared represents the whole. Okay? But if you only want a piece of it, here's what you do. You put in this theoretical angle, which represents how big you want your pizza slice to be. That's going to be theta out of the entire slice, because remember, a full circle makes 2 pi. So the theta represents how big you want your slice to be out of the entire pi, or the entire 2 pi, I should say. Okay, so if you do a little math here, you'll notice that the pi's cancel out. That 2 is left on the bottom, but can be written as 1/2. And then you have this theta r squared left. So this is the area of a sector, okay? So remember, theoretically, we could squeeze in an infinite amount of sectors to fill in the gaps, right? So if you want the true area under a polar curve, this theta is getting theoretically smaller. So what you do here is you call it d theta and you integrate. Integrating causes that theta to become infinitely small, so you could squeeze in an infinite amount of pizza slices, okay? That 1/2 is a coefficient that can go on the outside, and you're really just left with r squared from some number to some number. And this is really your formula right here. This is the one that we're going to be working on for today. Okay, your radius is really just your function. Okay, so these are straightforward. In regards to how does it get difficult, the difficult part here, you guys, I'll tell you right now, are your bounds. But I'll show you a way that works every single time. Okay, so here's our formula. That's what we're going to be working with. The 1/2, please do scoot it outside. It just makes it a lot easier to look at and to deal with, okay? Okay, so there's a rule with Rose curves. A Rose curve is basically when you have sine or cosine of something theta. So for instance, cosine of 2 theta is a Rose curve. Sine of 3 theta is a Rose curve. Sine of 8 theta is a Rose curve. So anything that has just sine or cosine of some multiple of your theta, you're going to get some type of Rose curve. And I'll skim through this real quick just so you can see. But these are Rose curves because it looks like a flower, right? It's very symmetrical. It looks like petals, right? So these are all examples of Rose curves, and we'll get to this, so don't feel like you have to draw this out, okay? So notice how they all have some type of symmetry, though, okay? Here we go. So here's the rule that's going to get you out of this situation fast, okay? This is to help you determine what your bounds are, okay? So I'll write it here, to determine your bounds. And these only apply to Rose curves. Later on in the next lesson, you're going to run into other equations that are not necessarily Rose curves. So know that this doesn't apply to all the other ones, just for Rose curves. Rose only. Okay? So, and I'll just use cosine here, but it applies to sine as well, okay? If you have the cosine of some even number theta, okay, versus an odd angle theta, okay? I think you guys know what even and odd are, but let me give you an example. So for instance, if I have the cosine of 2 theta, 2 is even, okay? 2 is even. Here's another example, cosine of 5 theta. You want to be able to figure out what the bounds are, okay? And just by looking at these angles, whether it's even or odd, it's actually going to tell you what these angles are, okay? So make sure that you write this down. Let me pull this up real quick, just so I don't shoot myself in the foot. Okay, whenever you have an even theta, okay, your bounds will always be from 0 to 2 pi. Okay, if you have an if you have an odd angle, you are always going from 0 to pi. This is your shortcut, you guys. Now, if you want to know the logic behind this, text me and I'll go through the proof with you. But honestly, I don't think it's worth the time. But if you're really curious, let me know, okay? And that's it, okay? Now, it does get a little bit technical when you get into the problems, depending on what they ask for, okay? So here we go. Find the area enclosed by one loop of the 4-leaved rose r equals cosine 2 theta, okay? Now, you don't have to worry about knowing what the curve looks like because almost always will they provide it. But if you're curious, you can go on to your calculator, turn it into polar mode, and I'll do this with you. Type in cosine 2 theta, but basically if you zoom in enough, it looks a little bit like this, okay? Don't you love how symmetrical that is? Pretty much there are 4 petals. Okay? These are terrible. Let me draw that again. 1, 2, 3, 4. A little bit better than last time. But let's assume that all of these petals are same in size, okay? And same in area in this case. So here's what you do. They're asking to find the area of one loop of the 4. So if I had to color this in, we only want to find the area of this one petal. So here's what we do. Area equals 1/2 the integral from a to b of r squared d theta. I'm going to write it out every time so that I remember it, okay? So let's plug in what we know. We know that area will equal the 1/2. Now we have to figure out our bounds. Okay, how do we figure out our bounds? Press play when you figured it out. Our bounds will be based on the number that's being multiplied with the angle. Since that 2 is even, take a look up here, I know that I'm going to go from 0 all the way to 2 pi. All right? R is the function. So this is something squared, d theta. In this case, my function is r equals cosine 2 theta. And that's it. Okay? But here's what I want to show you guys. This in yellow, and this is the key part here, all of that is calculating all of this yellow right here. Notice how it's covering everything, but they're really just asking for that red region. So naturally, how would you guys find just one petal? Press play when you're ready. So really what you're doing here is, if you only want to find one petal like they asked, then you would divide it by 4 because there are 4 petals. Okay? So on Delta Math, it's a little bit weird. They ask you for the bounds A and B. Okay? And then they ask you to write the integrals. So another way of writing this is 1/2. That divided by 4 can be scooted out as 1/4, and then the integral. So this is really just 1/8 integral from 0 to 2 pi cosine of 2 theta squared d theta. Okay? And then you plug in chug. All right? When you guys go to your calculator, make sure that you're in function mode. Okay? Go ahead and try to type this one out. I'm going to do the same thing here. And make sure you're in radian mode. Okay, so 1/8 math 9, 0 to 2 pi, parentheses cosine 2 theta, closed, squared d theta. So here I get approximately 0.393 if I round it. If you didn't get that, please do let me know. Okay? And that's it. Okay? What you guys do have to pay attention to is what they're asking for. Sometimes they ask for all the leaves. Sometimes they ask for just one of the leaves. You got to read it. Okay? All right, here we go. Here's example 2. Okay? Oh, and by this time, if I didn't give you the packet so that you could just print it, please do let me know, okay? You're more than welcome to just write all of this down. Okay. Let R be the region bounded by the rose curve. R equals 8 cosine 6 theta, as shown in the diagram below. Find the area of the region using a calculator. So my question to you guys is, are we looking for all of the petals or just one? Okay, so here, because it's so nicely illustrated, notice how they shaded in everything. Okay, so we need all the petals. So here we go. Try this on your own. Press play when you're ready. All right, here we go. A equals 1/2. Okay, so bounds. Are we going from 0 to pi or 0 to 2 pi? we will be going from 0 to 2 pi because, stop it, there we go, because that 6 next to the angle is even, so we know we're going to go from 0 to 2 pi. Okay, now if it was an odd number, you guys would just go from 0 to pi. Okay, r squared, r is 8 cosine 6 theta squared d theta. Okay, the rest is plug and chug. All right, now we don't need to divide by anything here because we want all the leaves. We want all the petals. Okay, so here's some advice. If you have trouble typing this part out, I would go to y equals and make your y1 8 cosine 6x or theta. I think x is easier. So if you go to your y equals on the upper left and you type 8 cosine 6x, once you quit, now when you retrieve y1, it'll be easier. So we're going to let y1 be that. So this is really just 1/2 math 9 from 0 to 2 pi of alpha trace y1 squared. That way you don't have to keep track of like the 4 or 5 sets of parentheses there, okay? So here we go, 1/2 times math 9, 0 to 2 pi, alpha trace y1 squared dx. I'm getting approximately, it's thinking, 100.531. And that's it. Okay? If you didn't get that, let me know. Obviously, the biggest concern is knowing how you set it up. If you're getting an error with the calculations, that's something that I could easily fix with you guys, okay? All right, let's try this one here. Let's call this C. Press play when you're ready. Okay, here, this will be a equals 1/2 integral. Now, since the coefficient of theta is 3 odd, I will be going from 0 to just pi. Okay? Function squared d theta. And that's it. Okay? Now, if you're going to use y1, if you're going to write it out, you can, but you have to declare it, especially on the AP exam. So let y1 represent 5 cosine 3 theta. So that way we could write it like this. A equals 1/2 integral 0 to pi of y1 squared d theta. Okay? I'll type this out real quick. Make sure that you guys actually change y1 if you're using the same calculator. Okay, so 1/2 times math 9, 0 to 2 pi, alpha trace y1 squared dx. I'm getting roughly 39.270 if I round it correctly. Okay, there's no need to divide because take a look, I'm looking at the entire shaded area, okay? Okay, so here's some other weird ones. Part D. Try this on your own. Press play when you're ready. Okay, here we go. A equals 1/2 integral. Since the theta has an even coefficient, that'll be from 0 to 2 pi. Okay, this will be the function squared, so 6 sine 6 theta all to the second power d theta. And then you're done. So if you notice, the setup's really easy. Now this here in yellow represents every single petal here. But notice how they don't ask for that. They only want 1 out of the how many do we have here, right? So if you counted this correctly, we have 12 petals. And we only want 1 petal. So we're going to go and divide the sucker by 12 because we only want 1 of them. All right? So that's the same thing as pulling out the 1/12, which makes 1/24 on the outside from 0 to 2 pi of y1 squared d theta, as long as you declare that y1 is 6 sine 6 theta. Okay? If you don't declare the y1 on the AP exam, they're not going to know what you're talking about here, okay? You can plug and chug, and I'll let you guys figure out that answer there. Let's keep going. Here's part E. Try this out. Press play when you're ready. Okay, so here we want A equals 1/2. Since the angle is multiplied with something odd, I know I'm going to go from 0 to pi. Radius squared, so 2 cosine 3 theta squared d theta. And I know that I only want 1 out of the 3, so I'm going to divide it by 3 here. Okay? So when I write this all out, first I'm going to declare that we're going to let y1 represent 2 cosine 3 theta. So this is really 1/6, 0 to pi, of y1 squared d theta. Okay? And whatever you get there. So again, we're dividing by 3 because we only want 1 out of the 3 petals. All right? Let's keep going. Part F. Take a look at the shaded region here, okay? You guys got this. It's something new, but you have enough to do this on your own, okay? Whenever you're ready. Okay, here we go. A equals 1/2 integral. Okay, this is going to be from 0 to pi because that 5 there is odd. Okay, this is going to be 9 cosine 5 theta quantity squared d theta. Okay, and again, that highlight right here represents every single petal, but you want half a petal. How the heck do you do that, right? So pretty much what you want to do is you want to divide it by 5 because you want 1 petal, and then you want to divide it by 2 again because you want half of 1 petal. That's the same thing as dividing by 5 and the 2, which is 10. Because it's 1 out of the 10 pieces. However you want to think of that, okay? So this simplifies out to 1/20, 0 to pi of y1 squared d theta. Don't forget to declare that y1 represents 9 cosine 5 theta. Now this here, using the y1 option, is that exactly that. It's just an option. But I do know that some people have trouble typing it out. So that kind of reduces the amount of errors there, okay? And then you get your answer. All right. I think I have, is this our last one? Shoot, let's do this one. Part F, G. I don't know my alphabet. Part G. Try this one here. Press play when you're ready. Okay. Area equals 1/2 0 to 2 pi because the 4 is even of y1 squared d theta, where y1 represents 2 cosine 4 theta. Okay, and I'm going to divide this by, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8 petals, but then I want to divide it by 2 again to get half a petal, so I'll divide this by 16. So the area here is going to be 1/32 of the integral from 0 to 2 pi of y1 squared d theta. So this method is foolproof with rose curves. Now, when you're dealing with other weird curves that's not rosy or rose-like, it's a different scenario, okay? All right, last one, and then we'll wrap it up. Part H. Try this one here. Press play when you're ready. All right, this one here is A equals 1/2 integral from 0 to pi, not 2 pi. The 5 is odd, so that's going to be 10 sine 5 theta quantity squared, d theta. And then I want 1, 2, 3, 4, 5. I only want 1 out of the 5, but I want half of 1, so that's divided by 10. Divided by 5 and divided by 2 is the same thing as dividing by 10. So this simplifies out to 1 over 20 integral from 0 to pi of y1 squared d theta, where we assume that we're going to let y1 represent 10 sine 5 theta. Plug and chug and compare your answers, okay? So Rose curves, it's that easy. We're building off of the symmetry and then we're just dividing out what we need, okay? Sometimes we don't need to divide at all. It kind of just depends on what they ask for. Okay? Text me if you guys have any questions, okay?